When you think about what's miles beneath our feet, it's easy to just picture rock and dirt, right? But down there are these incredibly valuable fluids, all under immense pressure. And figuring out what they are, well, that's a multi-billion-dollar challenge. It all boils down to one thing: capturing what we call the perfect sample. So today we're going to dive into the amazing tech that actually makes this happen.
So this is really the core question, isn't it? How in the world do you grab a bit of liquid from a place with crushing pressure and crazy high heat, haul it all the way up to a lab on the surface, and somehow make sure it's exactly the same as it was down there? It's a huge engineering puzzle, and we're about to break down exactly how it's solved. And believe me, the stakes here could not be higher. We're talking about billion-dollar investment decisions that hang on the analysis of these fluids. A single bad sample, just one tiny little change in its makeup, can lead to absolutely catastrophic financial and operational mistakes. This isn't just some lab experiment. It is high-stakes engineering at its finest. Now, this goal, it has a very specific name: a representative sample. It sounds simple enough, but this definition is basically the holy grail for reservoir engineers. It means the sample you're looking at in the lab has to be a perfect, identical twin to the fluid that's still miles underground. Anything less is just, well, it's a contaminated and frankly useless liquid. The fundamental problem here is actually something we've all seen before. Just think about a can of soda. All that carbon dioxide is dissolved in the liquid because it's packed in there under pressure. The second you pop that top, the pressure is released and, fizz, you get bubbles. It is the exact same principle with reservoir fluid. The moment you start bringing it to the surface, the pressure plummets, and all those dissolved gases just want to burst out, instantly ruining that perfect sample. So how do engineers fight back against us? Well, the very first line of difference is the equipment that physically goes down into the well. And it's not like there's one magic tool for every situation. It's all about choosing the absolute right instrument for the specific conditions you're dealing with. This chart gives us a really great high-level look at the trade-offs involved. You see, if you sample too early, you risk contamination. If you sample later, you risk that dreaded gas breakout. And sampling during production, that requires extreme, careful operation. So how do engineers solve these problems? Let's start with that first one: contamination. Okay, so our first major enemy is contamination. Before you can even begin to worry about pressure, you've got to be absolutely sure that the fluid you're capturing is actually from the reservoir, and not something you accidentally brought down with you. Here's the thing: the very act of drilling a well contaminates the rock immediately surrounding it. The fluids you use for drilling, it's called filtrate, get forced into the formation. So if you just go and take a sample from this area, you're not actually sampling the reservoir. Nope, you're sampling a mix of reservoir fluid and your own drilling chemicals. The solution is an incredibly smart tool, like the Modular Formation Dynamics Tester, or MDT. This thing is brilliant. It uses sensors, like an optical analyzer, to literally watch the fluid in real time. It can detect the difference between the pure stuff and the contaminants. And, this is the crucial part, it can then pump out and just discard all that contaminated fluid until it senses it's finally drawing in a pure representative sample. Okay, so we've got ourselves a pure sample. Awesome. But now we're facing that second huge challenge: how to stop the fizz. How do we get that pristine fluid into our sample chamber without the pressure drop that causes all the gas to bubble out?
All right, there are basically two main schools of thought here. The circulation type goes in the well open. The huge advantage is that there's no pressure shock when you take the sample. But the big downside is a massive risk of contamination if that chamber isn't cleaned out perfectly. The more common approach is the admission type. It goes in all sealed up and clean, but now you have to deal with that one critical moment when you open the valve to that high-pressure reservoir.
And that right there is the moment of truth. You've got this perfectly clean, sealed chamber. You activate the tool, the valve snaps open, and that high-pressure fluid just wants to rush in, which creates a kind of vacuum effect right at the entrance. That sudden drop in pressure is exactly what causes the gas to flash out, destroying your sample at the very instant you're trying to capture it. The solution is honestly pretty ingenious, and it all comes down to control. As the sample fluid enters, it starts pushing a piston. But, and here's the really clever part, this piston can't just fly backwards. It has to force hydraulic oil through a tiny, precisely engineered hole called a regulated orifice. This whole mechanism acts like a brake, slowing the piston way down and making sure the sample enters the chamber slowly and gently. No pressure shock. It's a beautifully simple mechanical solution to a really complex physics problem.
So we did it. We've beaten contamination and we've beaten the pressure drop. We have a perfect sample trapped inside our tool 2 miles underground. But you know what? The mission is far from over. The journey to the lab is just as perilous.
See, the sample is still sitting inside that downhole tool. It now has to be transferred into a shipping bottle. And this transfer, it's yet another point where a sudden pressure drop could ruin absolutely everything. You have to move that liquid from one container to another while keeping the pressure constant the entire time. For that job, you need another specialized piece of gear, the transfer bench. This whole device is designed specifically to move the sample at a perfectly constant pressure. What's really smart is that it lets the operator measure the sample's bubble point. That's the exact pressure where gas will start to fizz out before the transfer even starts. This way, they can make sure they stay safely above that pressure and keep that sample perfectly intact. So finally, the sample is in its shipping container. And listen, these are not just any old bottles. They're officially classified as mobile pressure vessels for transporting hazardous materials. They're subject to incredibly strict international regulations, and they can only be handled by highly trained personnel. It's serious business. This brings us to the last and maybe most critical parts of our story: safety during transport and what's next for this technology. Because the engineering challenges, well, they don't just stop once the sample is sealed in the bottle. This next big challenge really comes down to high school physics. Remember the ideal gas law? Pressure and temperature are directly linked. So a bottle that was filled down in a cool well might end up sitting on a hot truck deck somewhere. As that temperature climbs, the pressure inside that sealed container can spike to incredibly dangerous levels. The containers themselves are actually designed to handle this. For gas samples, engineers will carefully calculate the maximum fill pressure to leave a built-in safety margin for any temperature increase they might expect. For oil samples, the solution is even more clever. They add a tiny calculated bubble of gas. This safety gas cap acts like a little compressible cushion, absorbing the pressure increase as the liquid expands from the heat. And of course, the technology is always improving. I mean, it never stands still. New monophasic samplers actually use a nitrogen precharge to overpressurize the sample, making sure it never even gets close to fizzing. And for just absolute ultimate purity, engineers are now designing tools from special inert metals that won't absorb any of the gases from the sample itself. It's just this constant, relentless push for a more perfect sample. So from fighting contamination miles underground to managing pressure changes with basic physics, getting that one perfect sample is a whole chain of incredible engineering solutions. It's just a reminder that billion-dollar decisions can literally hinge on a single perfectly preserved drop of liquid. And as we start to explore deeper, hotter, and more extreme reservoirs, you have to wonder, what's next? This quest for the perfect sample is only going to continue to push the boundaries of what we think is possible.